Let us begin lecture 18. We discussed concentration cell in brief, and then we attacked a problem on corrosion under rainwater droplet, and then we explained that at the center position, after some time, at the center position becomes preferentially anode, and the annular portion becomes preferentially cathode because we have more oxygen there. So, their cathodic reactions would happen and they would act as cathode, and the center portion anodic reactions, that iron would go into iron plus as well as iron plus 3. And those iron plus 3 as well as plus 2, they will combine with H minus, that is the product for this product in the reduction reactions of oxygen in combination with water. So, they will form ferric hydroxide or ferrous hydroxide, and they will deposit around that center positions. Now, you might have seen that in some cases, if let us say some handle, a metallic handle is fixed on a wooden block on the door or some places in the window, and you might see that if you after some time, after some years, if you take that particular metal block out, the portion where the screwing has been done, and if you watch the screw carefully or the nail carefully, you would see a nice observation if you have observed before. I have brought 2 samples. Let us see whether we can see something, and then we can have a direct correlation on this concentration cell and the differential aeration cell that develops due to the difference in oxygen concentration. Now, first example I am showing this one. If you see, this is a broken wood, it was nailed here. This was fixed on a particular, this particular broken wood was fixed on another block with this nail. This was a nail, or rather it is a screw. This is a screw. If you see this cut, you can see this cut. So, let me put a pin, and then if you see this cut, so this is the cut. So, that means it is a screw, and see the top part of the screw, it is corroded, there are red rust, there is a signature of red rust. But once you see this the rest of the part which are going inside the wood, let us say this part, if I see this part if I carefully see, let me put a light on this. So, then it will be clear. If you see this, let us see this, you can see it carefully. Can you please zoom it little more? Is it possible to zoom? So, I am talking about this nail part. This is the nail I am talking about. The rest of the screw part, it is seriously corroded, but top part which is exposed to the atmosphere is corroded, but that not serious. This also can be explained from difference in oxygen content. Now, let us see another one. If we see this one, this is more severe. This is a metal object, and there are screws here, there are 2 screws here and 1 screw here. Okay. So, almost similar type of screw, 1 screw is missing because when I pulled it up and then 1 screw got missing. But if you see this particular segment, this screw top, there are corrosions. I am not saying that there are no corrosion, there are corrosion. But interestingly, if we see the other part, if we see this, you see it is a kind of exfoliation. This screw, the rest of the screw has swelled, and this swelling has happened because of this iron hydroxide and iron hydroxide formation. This is a rust, these are basically the red rust. And if you see this one, some part has vanished because the corrosion was so severe, the some part has vanished because it got lost into the atmosphere, not into that particular, it remained in that particular wooden part, because it was fixed like this on a wood. So, this is a wood and this was fixed like this. Okay. So, now why there is a little bit of corrosion on top, but the part which has entered into the wood, there we see lot of corrosion. So, why? So, this can also be explained by using this concentration cell. Now, if I see this top part, the top part is exposed to the environment. Yes, there are moisture, there are oxygen, but the bottom part which has entered into the wood, though we assume that the wood also the wood is pervious, because there are fibers, that fibers can have moisture, or even the moisture can enter into the wood over the time, and but the oxygen content on top and so that means we have electrolyte, they are basically electrically connected, because here also we have moisture, here also we have moisture, because the wood contains moisture, or over the time the moisture can seep in, and this part of course we have moisture. At the same time we have oxygen here, but the oxygen content in this zone will be very less. So, here we have a maximum oxygen, but as we go towards depth, the oxygen content would reduce drastically. So, that means this zone that's at the extreme part would be anode, but the top part where we have more oxygen. So, cathodic reaction, which is oxygen reduction in neutral media. So, that reaction would happen on this entire surface, but the bottom part where we do not have oxygen, that becomes my anode, and since iron dissolution, iron goes into iron ions, they are strong anodic reactions, those reactions would happen here, and then those iron ions that are forming, they will combine with this OH minus that are forming, and they form red rust or hydroxide or hydrated oxides of iron. So, this is again can be explained from the point of concentration difference of oxygen. So, this is a classic example, you might also see at several locations such kind of things happen. So, now this is what I wanted to say, that concentration cell is a serious consequence. Even crevice or pitting corrosions, these two are very serious forms of corrosion, as we have explained before, because they are localized, extremely localized, and they are also related to the concentration difference of oxygen. So, in the crevice part there will be oxygen depletion, and away from the crevice part we have still oxygen. So, the crevice part becomes preferentially anode, and the crevice section away from the crevice section, they will act as cathode. So, the crevice part would corrode, the cathodic part, the rest of the part would corrode less. Similarly, pitting also, in the pitting zone we have preferentially anode and preferentially anodic reactions or iron dissolution, and then formation of iron oxide or iron hydroxide they would form, and the rest of the part would remain as cathode, because there we have more oxygen. So, these are the kind of examples what we find in our day to day corrosion phenomena. Now, in lecture 18 we will look at that, see these corrosions are taking place because of the ions formation, and then we have a concentration cell development and oxygen effect, oxygen content it can change in a short region, and then we can have cathode and anode, all those examples we have put up. Now, finally, we have to see that when a metal oxidizes or corrodes in a particular aqueous medium. Now, when we talk about aqueous medium, in the beginning we concentrate on presence of moisture or water, and when we talk about moisture or water, we have to talk about pH level, or pOH level. So, now we will consider the presence of metal ions, metal, pH and water. So, when we have this kind of system which are commonly observed, okay, so there we have to see at what condition we have corrosion of that particular metal. Now, when we talk about this what condition, that initially we talk about the thermodynamics part. That means, initially we have to see whether the free energy change for that corrosion process is negative or not. When the corrosion process free energy change is negative, we say that the corrosion is spontaneous. Otherwise, if we see that the free energy change becomes positive, then we may say that we will say that the corrosion process is not spontaneous, rather it is difficult, rather thermodynamically we will say that it is not feasible. So, let us have some examples. For before that we see this particular plot. This particular plot is a serious plot, and I want you to understand this plot, and time to time this plot has come in this particular set of lectures. So, we see delta Z0, E0 and K. K is the basically equilibrium constant. So, now relation between these arms basically ln K equal to NF E0, and here it will be delta Z0 equal to minus RT ln K, and here delta G0 equal to minus NF E0. So, these are the relations between the arms. Now, if we try to see, let us say delta Z0 equal to 0. Now, for a particular equilibrium reactions, let us say this is my equilibrium reaction, I am considering N, Ne equal to Mn plus. So, this is the reaction what we talk about. Then if we consider the standard free energy change delta Z0, that means P equal to 1 atmosphere, T equal to 298 Kelvin, then K would be 1. So, K is nothing but activity of Mn plus by activity of M. Now, when we have this one to be 0, then we see E0 ox red equal to 0. So, here what you see LD not equal to 0, that means you can use this formula equal to minus RT ln K as well as delta G naught equal to minus NF E naught. So, you could see that if this goes to 0, then this has to go to 1 and this has to go to 0. That is what we have seen. Now, the second condition what you can experience, where you take delta G naught less than 0. Now, if you take less than 0, that means K has to be greater than 1 and E naught should be greater than 0. Why? Because if you use this general formula minus RT ln K, so K has to be greater than 1, then only this can go to negative, and if it goes to negative, since there is a negative sign here, so that is another formula which is NF E naught red ox by red, that means reduction potential we are considering. So, that case if this is less than 0, then since there is a minus sign, so this has to be greater than 0. If K is greater than 1, that means the reaction should move towards forward direction. Okay? This reaction should move towards forward reaction, forward side. Okay? Since K is greater than 1 and K we have found out from this equation. So, that means activity of metal ion concentration has to be more than the activity of metal. So, then only you could see that the K should be greater than 1. So, this is case 2, and there could be a case 3 where delta G naught would be greater than 0. Now, if this is greater than 0, we know this general formula, which is minus R T L and K, K is the equilibrium constant. Now, that time, since this is greater than 0, then K has to be less than 1, then only this can go to this del G naught can be would be greater than 0. So, K in this case should be less than 1, and delta G naught again equal to minus N F E naught. So, which is ox by rad. So, that time, since this is greater than 0, so E naught would be less than 0. So, that means the reduction potential would go towards the negative side. So, that means here K would be less than 1 and E naught ox by rad, which is reduction potential, would be also less than 0. Fine. So, that means here we have the backward reaction, which is metal ion reduction will be preferred, and here metal ion reduction or cathodic reaction would be preferred. So, that means the forward reaction would be less probable, and the backward reaction, that means this reaction becomes more probable if we have this situation, and that time we have this. So, that means the potential would go towards negative. That means the cathodic. So, that means we have less amount of this reaction. So, that means metal ion would not be formed, rather metal ion would get reduced. So, when we say that metal ion would get reduced, it means that the corrosion process, that ion formation process would not be a probability, rather deposition becomes my probability. That case we might say that the corrosion is controlled or corrosion is minimized, but in this case corrosion is maximized, okay. And in this case it is equilibrium. So, the corrosion as well as metal deposition, they are happening at the same rate. So, these three situations, this is situation 1, this is situation 2 and this is situation 3. In fact, situation 2 and 3 would guide us whether the corrosion would take place or not. Now, when we talk about normal system, that means let us say nickel in H2O of certain pH. So, nickel might get oxidized, that means nickel can form nickel ion. So, that means it is a corrosion, or it can go back and form nickel. So, that becomes my cathodic reaction or less corrosion. And that time, since these are all the standard states, that means E0 as well as D0, we are talking about standard state, and in the actual system we may not maintain standard state. So, the nickel concentration in water may not be 1, that activity of nickel ion may not be 1. So, that times we have to consider non-standard situation. In the non-standard situation, we have the similar kind of analysis. So, that time we have to consider this equation. It is Q or the activity quotient. So, Q can be written in the form of activity of N plus activity of M. So, we are talking with reference to this reaction. So, there we are having a non-standard free energy change. And then we have to consider this value, we have to, if we see this goes to is greater than 0, that means the forward reaction or corrosion reaction is not feasible. And if delta Z less than 0, that means corrosion process is, and here we are considering with reference to the corrosion. Okay. So, that case this would be a feasible process. Now, our interest would be to find out with the data set what we can generate from this to see whether this is greater than 0 or this is less than 0 at that particular condition. See, in order to know this, we have to have a numerical problem, and then we would be really clear that yes, if we have this condition, that means this is the pH level, this is the temperature, this is the pressure level, then we can decide that whether a particular metal would corrode in that particular solution. And when we talk about corrode in that particular solution, that means the corrosion process becomes spontaneous. And when we talk about spontaneity, we have to consider free energy change, and we have to say this condition is met. Now, in order to do that, we will take up a problem. That problem I am taking from a book which is a very good book, Principles of Corrosion Engineering and Corrosion Control by Zaki Ahmed. You can read this book, this is a fantastic book. I will just take one problem from that. So, the problem statement says that calculate the theoretical tendency of nickel to corrode in deaerated solution, deaerated water where pH equal to 8, and assume the corrosion potential, corrosion products are H2 and NiOH whole 2. Data given KSP for NiOH whole 2 equal to 1.6 into 10 to the power minus 16 E0 Ni plus plus Ni equal to minus 0.25 volt. Temperature of course is 298 Kelvin, pressure equal to 1 atmosphere. So, now it is saying theoretical tendency. The theoretical tendency, whenever we are talking about theoretical tendency, we first consider that nickel is corroding. So, nickel 2E equal to nickel plus plus, this reaction is taking place. And then we will see that if this reaction happens, then we have to find delta G0 for the entire system should be less than 0. So, then we would say that the nickel corrosion is spontaneous. So, this is corrosion. But if we find delta Z0 delta Z greater than 0, then we will say that this is non-spontaneous and this is spontaneous. We are talking about corrosion of nickel. Now, we are talking about, so when we say that entire system, so not for this particular reaction. So, we have to see the another reaction which takes place, because this is my anodic reaction. So, we have to have a cathodic reaction. So, cathodic reaction is this. So, now if I do this, so if I add them, so then it becomes Ni plus 2H plus, it goes to Ni plus plus H2. So, this is my total, this is my overall system reaction. That means, there is a equivalent cathodic as well as anodic reaction. So, this is my cathodic reaction. But in addition to this, we see that NiOH 2 is forming, and it has got a very low solubility product. So, that means, these Ni plus plus, this Ni plus plus will react with OH minus that is there in the water system already, because water we can also dissociate H2O, it goes to H plus plus OH minus. So, this reaction we can consider. So, when we consider this reaction, then we have to also take care of Ksp of this H2O. So, the Ksp of F 10 to the power minus 14. So, this 10 to the power minus 14 we can write H plus into OH minus equal to 10 to the power minus 14. So, if we take log, so log of H plus log of OH minus equal to minus 14. So, if we take minus log of H plus and minus of log of OH minus equal to 14, since we have one H plus and one OH minus, so we can assume that the number of H plus and number of OH minus would be equal. So, then this and this they would have equal contribution to this 14. So, I can say that, and this is nothing but pH plus this is nothing but pOH equal to 14. Now, if we have 7 and 7, then it becomes 14, and we have, if we have a neutral solution, that time the pH is 7. So, that is what we have, pOH is also 7. Now, here we have pH equal to 8. So, that means H plus concentration is nothing but 10 to the power minus 8, since minus log of H plus equal to 8, and that is what the concentration of H plus I can find out. So, now if I find out H plus, then I can find out OH minus into H plus equal to 10 to the power minus 14. So, I know what is the concentration of H plus ion. So, I can find 10 to the power minus 14 equal to 10 to the power minus 8 to 10 to the power minus 6. So, I know the concentration of OH minus. Now, once we find out OH minus, now this OH is available to react with, this OH is available to react with Ni plus plus, and when they react they form whole 2. So, now it will also have its own equilibrium. Now, there the amount of nickel plus plus that is available in the system would be decided by the Ksp of NiOH whole 2, because once NiOH whole 2 forms, the limited solubility of NiOH whole 2 would allow little bit of nickel plus plus ion to be present in the solution. And once we know the concentration of nickel plus plus in the solution, then we can find out what is the potential that would generate for this particular reaction, in that particular solution. And also we know pH, so we also can find out E1 and E2, and then we can have a difference between these two potentials, and that would lead to finding out these two situations. So, we will discuss this same problem in our next lecture. For the time being, we know that we have to go through this route to find out the nickel concentration, nickel ion concentration in the solution. Let us stop here. We will continue this lecture in our next class. Thank you.